So far, we have seen topics on compensated design based on root locus, based on Brody, and all the design requirements, whatever we need to make our system behave in a specific way. Now we are going to move forward to a different structure. So far, we had been using transfer function in all the previous 9 weeks. Now we are going to introduce a different representation of the same system in terms of state space equations. So transfer function and state space equations go in one in hand. Actually, this is a yet another way to represent a system which is in a more sophisticated way when you go for a higher order system or when you go for a different input, different orders of outputs of any system. Okay. Now, the idea behind this upcoming lectures are how you can represent a system in a state space form. What are the more advantages than the transfer function? So far, we have done. And what are all the new things we can do when we represent the system in a state space form? That's what we are going to cover in this week 10 to week 12. Right. So, these are some recaps you are familiar with, and this is a system example system mechanical system we have taken. So we have seen this system when we are studying about the transfer function. It's a mass spring damper system where we represent this in terms of m is a mass, b is a K is a spring and B is the damper, where X is the position and F is a force you are giving to that system. When representing in terms of transfer function, we will be using this X of S divided by F of S, that can be elaborated into Laplace transform of output divided by Laplace transform of input. Whatever you have in the right hand side, that we call it as transfer function. Now we are introducing a new representation here in terms of state space equations. State space equation can be written in terms of a differential equations, or it can be written in terms of a matrix form, just with the in the same differential equation form. Now, how can we convert this to this? How can we represent a system from a transfer function to a state space equation? That's what we are going to see. For example, if I'm taking the same system, x of s divided by f of s, which is 1 by ms square plus bs plus k, right? Here, x of s is the position, f of output, and f of s is the input force. Now, if I rewrite this equation in this mx square plus bs plus k into x of s equal to f of s. Right? Now, take inverse Laplace transform. So far, we have been using Laplace transform. Now, I want to convert this back to the time domain. So, if you take the inverse Laplace transform, in between steps, I'm writing for you to understand this properly. Equal to f of s. We know Laplace transform of x dot is equal to x dot of t equal to s into x of s minus x of 0. Here there is no mention about x of 0. Why? Because transfer function, when you write a equation in terms of a transfer function, you are assuming it there at zero initial condition. The transfer function definition itself will hold at zero initial conditions. So whenever you are representing a system in a transfer function format, you are assuming x0 or x of 0 equal to 0. So you are starting the system from 0 always if you are representing the system in terms of transfer function. So always this x of 0 goes to 0 when you represent in transfer function, right? So I'm just considering this. So when you consider this m s square, this will be x double dot. All the initial conditions x of 0, x dash of 0 will go to 0 plus b into s x of s will be x dot plus k into x of t. I'm taking this x of t as a whole because there this is also x of t, right? Oh, not right. Right. M x double dot of t plus b x dot of t plus k x of t, right? Equal to f of t. This is what we will get when we write in terms of a Mm, dynamic equations, right? Now, I want to represent this in terms of a matrix or a differential equations. How can I write it? First, we have second order system, right? Because it has x double dot. X double dot represents there are two energy signals. It comes to s square when you take a Laplace transform. It's a second order system. So this x double dot is also a second order system. This represents, we already know that order is equal to number of energy storing elements in the system. So we know in this system, we have two energy storing element, two orders we have. Now, when you want to represent this in terms of a differential equation, then you know the order should be 2, right? That's what it is here. I want to convert this nth order differential equations into n single order differential equation before converting it into a state space equation. This is an important step. First step to convert from a differential equation to a state space form. So whatever the order is, nth order, it can be third order, fourth order, fifth order. Nth order should be converted into n single order. So second order system should be converted to two single order system. Third order should be converted to three single order system. Likewise. So I have to convert this nth here in our case, this is second order to two single order system. How can I convert? First, you have to assume a dummy variable x1 equal to x. Consider a dummy variable because you need a two order system. So there should be two variables x1 and x2. So first you assume whatever variable you are taking. Here we are taking x. That's why you are assuming x1 equal to x. So automatically x dot equals to x1 dot. What about x2? So if there is
Double dot can be
yeah, exactly. So this should be the x1 double dot, right? X1 double dot should be equal to x2 dot. It's a kind of differentiating the same variable again and again until you get your number of orders. So I got two elements for representing my state space equations, x1 dot and x2 dot. If your system is a third order system, you have to write x3 dot also. That will be x2 double dot. Okay, likewise. Now, what is here x1 dot is equal to x2 because this x dot I'm assuming is a x1. If this is a x1 dot, then this will become x1 dot becomes x2. So this is the first primary equations. The second equation would be x dot x2 dot will be equal to whatever you have in this side, you have to keep it there over that side. For example, I have this, wait, I'll remove this and write it again here. Where can I write it? This is a mx dot plus bx dot plus kx equal to f. Small f means f of t. Okay, right. Now I am writing in terms of m x1 double dot plus m b x1 dot plus k x1 equal to f. Now I'm going to replace it directly. So this x1 double dot will become x2 dot plus bx1 dot plus kx1 equal to f, right? Now I'm keeping x2 dot here and taking everything else this side, x1 dot minus kx1 plus f whole by 1 by m because here there is a 1 by m. So this is going to be my second equation. So here this is my second equation. So I got both x1 dot x2 dot to represent my system in terms of a state space equation. Now I'm collectively writing it here. x2 dot is equal to minus b by m.
one question.
What?
One question I wanted to ask.
Yeah,
Why
yeah.
are we writing x2 dot? Why not just x2?
We need to represent this in terms of state space equation, right? State space equation generally represents how your system, it's actually a collection of previous states. So, it tells your state trajectory. For example, if you take a causal system, right, I'm writing it here. If you take a causal system, how it will be? Causal system can its present output can depend on present input and previous input, right? So if your system is a causal input, you if there is some previous input, some history of input, you have to save it somewhere. You should know what are all those previous input. How will you know? For every system you cannot, like in practical case, you cannot keep a recorder or some other memory storing devices to do this, right? So practically we can explain this previous set of inputs as a straight trajectory. So even with only one state, x1 or some x state of the system, it knows that how the system was previously. So your state information holds about your history of the system, when from where it started and now at what time steps it is at what location. So that state trajectory, the entire history of your system, you can take from the state trajectory. So if you want to know a previous system, how will you know the differentiation? Differentiation means what? If I want to differentiate something, it is essentially meaning x2 minus x1, right? So some previous input should be there. If I want to represent any system, I should represent it in terms of a state trajectory. For that, you need differential equations, not a single variable like x2. You need a differential equation that tells x2 dot or x dot or y dot. So you need the reference trajectory or trajectory of the states. That's why we are using dot instead of a single variable x2. Is it clear?
Yes, ma'am.
Right. Okay. Um, So we'll continue writing the system state minus k by m x1 plus f. That's it. So this is your state space equation. It's very simple. So first of all, you have a transfer function. First step is to convert nth order differential equation into n single order differential equations. So once you convert that, assign variables, some variables, whatever the state or system representation if you have. For example, your system can be represented in terms of y, but you can assign it to x1, x2. Just you should know what are all the states, like what is x1, what is x2. I can take x1 as x, that is position, x2 as v, velocity, x3 as acceleration. So similarly, when you write in terms of like this, x3 dot will be a, x2 dot will be v, x1 dot will be x. Does it make sense? Because differentiating this will give velocity, differentiating this will give me acceleration. So likewise, you have to choose your states according to your system representation. So these are all the two steps you have. First step is to um, convert nth order differential equation into n single order, then assign variables like x2, x1, y1, y2, whatever you want to name it. But remember to keep the same representation throughout this problem, right? Then you will get n different differential equations. Then you can keep it as it is. Otherwise, you can write it in terms of a matrix representation. I hope this part is clear. If you have any doubt, you can ask now. Otherwise, you can post it in the discussion forum. So that's how we got this. So whatever I raised it, whatever I wrote it here, that is what it's been represented in terms of matrix equation here. Okay, what is this? So in general, you won't only represent a state of a system, you will represent the output also of the system. Your collective pair of state space representation would look like this. X dot is equal to AX plus BU, where X is the state, U is the input, and another pair of this is Y is equal to CX plus DU. Most probably this D would be 0. So unless and otherwise you mention is explicitly, this D would be 0, because this whole state representation explains about your state, your input behavior and output behavior. So whatever you want to make from input to state, how the system would be, that you can learn. From state to output, how the system would be, that you can learn. From input to output, how the system would be. That kind of studies can be done using this state space representation. So state space representation always comes in pair, that is x dot is equal to ax plus by, y equal to cx plus du, these two pairs, right? Now, so that's what they have explained it here. So we already have seen how to convert this to this form. Now another example they have given in terms of simple pendulum. So simple pendulum is also a second order system. Theta dot plus b by ml square theta dot g by l sine theta. So theta is the variable here. So I can take theta equal to x1. So theta dot would all like be x1 dot, then x1 dot is x1 double dot is equal to x2 dot. So automatically my x1 dot is equal to x2, x2 dot is equal to, I'm just keeping the second order differential equation here and moving everything aside, b by ml square theta dot plus g by l sine theta plus t, right? Now theta double dot would be, this is x1 dot is equal to x2. This is x1 double dot means theta double dot equal to x2 dot. So theta double dot can be replaced using x2 dot, right? So x2 dot is equal to, I'm just rewriting this equation, x2 dot is equal to minus b by ml square. Theta dot can be x2 or x1 dot. I'm just keeping it x2 because to keep as a same variable, plus g by l sine theta is equal to x1. So it is x1 plus t. If this is too much here, I will write it here. See, theta double dot equal to, there is no equal to here, theta double dot plus b by ml square theta dot plus g by l sine theta equal to t. This is the original differential equation representation, right? Now this is a second order system. We want to convert this to first order systems, right? So how can I do that? First, assign a variable. First point is converting to nth order differential equation to n single order. Second is to assign a variable. How can I assign a variable? Theta equal to x1 I'm taking. So if theta equal to x1, theta dot, differentiate both sides, x1 dot, right? Theta double dot equal to x1 double dot. Now it is clear. I'm going to assign this x1 dot, that is theta dot, to another variable x2. So automatically double differentiating this will give me x2 dot. Now I have theta double dot, so I'm keeping it theta double dot here and putting everything to the right hand side, ml square theta dot, just rewriting in terms of theta double dot one side and rest of the things on the other side. Sorry, this will be plus sine theta plus p, right? Now just replace this theta with whatever variable you have assigned so far. Theta double dot is
I
x2 dot.
want it be minus g by l sine theta.
Yeah, right. It's minus z by L. Sometimes I will make this mistakes. Let me know, okay? Right, good, thanks. Now this will be b by ml square. Theta dot can be replaced by x2 minus gl by sine. Theta will be replaced by x1 plus t. That's it. One equation we have written, x2 dot is there, then x1 dot is equal to x2 simply. Every time it will be like this one. So we have two differential equations. You can either keep it like this, otherwise you can write it in terms of a matrix equation. That will give you the same system in terms of state space representation. Similarly, you can play around using this DC motor. This DC motor equation we have done in while studying transfer function. Now you can replace it using your variable assigning. Then you will get a matrix form. This is of third order system. So there will be three states. So this explains what and what. Just you can read through it. What is A? What is state? What is input? And what exactly the A matrix represents? A matrix is the system matrix. So it holds all the information about the system states. B matrix is the input matrix. It holds all the information about your input to the system. What kind of input, step or ramp or sinusoidal, whatever information you are giving, that will be there in this system. And C matrix is the output matrix. What kind of output you can expect out of the system, that will be represented using this matrix. Usually, the difference between the transfer function and the state space is both are useful. You cannot neglect one and choose another one. But in terms of when we can use transfer function, when we can use state space. Transfer functions are handy until it reaches third order system. Second order is most handy. Until it reaches third order, it's fine. We can manage. But more than that, it's very difficult to handle. And another thing is when it comes more than one input, one output. One input, one output, single input, single output system, we call it as single input, single output. When it goes beyond this, we call it as MIMO, MIMO, multiple input, multiple output. So if you have a transfer function, for example, y of s divided by u of s, some transfer function representation a square plus s plus 1 you have, then this tells this is one output and it has another corresponding input, right? So when it comes to two input, two output system, let's take, then you have to represent y1 by u1, y2 by u2. Then you have to tell how y1 affects due to u2, how y2 affects due to u1. So there will be mix and match. So for example, a two tank system, if you take say for an example, then you have to say first input how it affects first output and second output. So the intermediate relationship also you have to hold. It can be represented using transfer function, but when it goes to more than two inputs, two outputs, it will be very difficult and it will be very tedious to calculate. So there comes the state space representation for rescue. So you can easily represent higher order systems in terms of matrix or with matrix properties using the state space representation rather than using the transfer function here. So it's more convenient representation in terms of this. That's what we are trying to use. Both Laplace transform, we can use it for transfer function and state space equations. There is no catch here. So it is convenient when you are dealing with higher order systems or more complex systems. That's why. Okay. Mm, yeah, general procedure to obtain a state space representation as we discussed earlier. So these are some example systems they have given. So this has two states, attitude and angular velocity of the satellite, theta and omega. So this is the relationship between the system states and the input and output of the system. If FC force is the input. So that's how we represents the input output relationship. This two. This is another example based on cruise control. Here you don't see X at all, right? X is indirectly bounded here. So the equation represents based on velocity V. V is what do you call it? Damper? Yeah, damper. And M is the mass. That's what the whole equation has. And one input U they have. So when you write in terms of state space, you would explicitly see X here. So you can visualize the state also. Here, from this transfer function, you can visualize how the velocity of the system would be, not the state. But in state space representation, you can visualize both state and the velocity, how it would look like. So that is a one good thing. So it is already a single order system. So you can represent it directly. Like x dot, this hidden state, you can take it in terms of v, and v dot you already have. So I'm just writing in terms of this minus b by mv plus u by m. That's it. So you have two states, so you can represent it like this. Okay. Now this is another example based on DC motor. Yeah. The another important thing is representing in terms of controllable and observable canonical form. The first question is, what is canonical form? Why do we need canonical? So in control theory, the canonical form is a standardized structure representation of a system state space model. 1 minute. Right. So this canonical form is a standard method to represent the system state space model. It will be useful for analysis, design, if you want to design a controller or observer in later part, and it ensures the properties like controllability and observability easily. So we will soon learn what is controllability and observability. Before that, we will see what is the representation looks like. So you have a transfer function. Our transfer function, what you use to deal with this proper transfer function, meaning the degree of numerator will always be lesser than degree of denominator. If this is equal or greater than, then it might be improper transfer function, right? So those kind of transfer function we won't deal with usually. Our zeros will be lesser than the poles. That is a like practical system we used to have. Okay, so this equation 17 represents the controllable canonical form. So if you want your system to be controllable, for example, um, like if where it was controllable canonical form, right? So first of all, this explains controllability. This preserves the property of controllability, this kind of representation. So observable, this is controllable canonical form. Similarly, there is a observable canonical form. This preserves the properties of observability. So why do we worry about controllability and observability? So the idea behind converting the transfer function representation to state space system is, in week 10 ahead and week 11, 12, we will be studying about designing a controllers, how we design a PID controller using transfer function. In terms of state space representation, what are all the cool controllers we can do, that we will see in later weeks, right? So to make the system controllable, it is there in the definition itself. So if this is a coordinate state, so my question is, can we try the system from any initial condition to any desired final state? For example, from 0 to, can I make the system to go here? It can take any trajectory. The only my idea is to drive my system from x0 to xf, from Chennai to Pondicherry. If I can do it precisely, can I take my car from Chennai to Pondicherry? That's what I'm worried about right now, to design a controller. Then I can come to a conclusion then, what is the shortest path, what is the speed my car should go, and at what time it should reach. Those comes next, right? First of all, can I take my car from Chennai to Pondicherry? This precisely from this point to that point. That gives me the idea about controllability. If you can do this, then you can say your system is controllable. Observability. Can we determine the internal states of the system from its output over time? For example, I have a black box system. I am giving an input, and based on that, I am getting one output. So I am asking, with the knowledge of this output alone and some states of this, if the knowledge of the output and input, can I know the system states? Can I get the whole idea of the all the states of the system? For example, if it's a second order system, can I know what is x2, what is x1, whether it is position velocity or different things, mass, whatever it is. So how should I know about it? Sorry, if whether will I be able to know about it? If I can know that, then my system is observable. Otherwise, it is not. Two questions. Can I drive my system from one point to another point, from an initial position to a final point? Then, if yes, then it is controllable. This property suggests it is the property name is controllability. That's it. If I give an input to my system and I'm getting an output, with the knowledge of output and input, can I know all my states? So this kind of study is called observability. So if I can know all my states with my output, then the system is observable, right? These are all the two things. So if this controllable canonical form and observable canonical form will preserve this property. It will, if you can convert the system to this form, then you can say my system is controllable, observable, kind of that. So this is one representation. Equation 17 is the controllable canonical form. Similarly, equation 19 is your observable canonical form. So you should be able to convert your transfer function to this format to make the system controllable or observable, or to study whether the system is controllable or observable for later part to design a controller or observers. Okay, good. And then so far we have studied how to convert from transfer function to state space, right? First one is nth to n single. Second is to assign variable. Then boom, you'll have a state space representation. Now the other way around, how to convert a state space to transfer function. So we have a ready-made formula that is derived using this conceptual understanding. So you have this C, you have the system matrix A, input matrix B, output matrix D, and C and D, right? So you will just have to write it in terms of this C into Si minus A, the whole inverse, into B plus D. So you should be careful here. This into this here it is summation, sum. So if you can write in terms of this and solve this, you will get a transfer function representation using with the help of the Laplace transformation. And similarly, whatever we have studied so far in a transfer function, if it is a y of s by x of s is equal to 1 by some equations, so we will convert this denominator, equate this denominator to 0, and we call this as characteristic equation, and we find the roots out of it, right? That is the pole of the system. That is what they are also representing. But in terms of if we represent in terms of state space equation, then this is the idea behind it. So here the eigenvalue of A will be equal to the poles of the system. If you take the A matrix, system matrix, and if you find the eigenvalues of this A, that is indirectly or directly telling that that is the pole of the system. The eigenvalue of the system matrix is your pole of the system. That's it. Simple thing. Eigen of A is equal to pole of system. So if you find the eigenvalue of a matrix, you will say what are all the poles you have in your system. Thereby you can say whether the system is stable or not. If everything lies in the left half, it is stable, right half it is unstable. So these are some examples they are giving. So from this, you are converting into a state space equation. Then you are finding eigenvalues, writing in terms of this, finding again the transfer function. So from this, you are finding the poles, sorry, eigenvalues of the system. You'll get -1, -2. Then this is the pole. So both are lying on the left half of the explain. So the system is stable. Right. Model 2 represents what is the important things we want to discuss here is solutions to the linear systems. So we, yeah, another important point when we want to discuss about the transfer function versus state space. Transfer function is explicitly for LTI system. State space can be for LTI or LTB. Linear time invariant or linear time variant. Both of the systems can be represented using the state space. For example, 0, 1, 2, 3. X dot is equal to x plus 0, 1 u. This is a LTI system. So I can easily represent the LTB system like this. So this T will vary with respect to time. This is a representation for a LTB system. We don't have to do any extra work for this. So that is another advantage of using the state space representation. It is easy to represent in state space equations. Okay. Right. This particular slides from here will tell how to find a solution to your linear system. So this is a linear state space, sorry, yeah, linear state space representation, Cx plus T. So they have given the dimensions of each and every state matrix so that you can know who, how, what are the dimension of your whole system. So they suggest how you can find the solution to this equation, x of t, right? So see, if I want to explain this, if I take this system, how will you represent in terms of so this will be x into x of s minus x naught, some initial condition. I'm not assuming it is to be 0. So I will have something like this. So this will become s minus a into x of s equal to x naught. This will give me x of s is equal to x naught by s minus a. So if you take a inverse Laplace transform, this will become e power at x naught, right? Whatever initial condition you are assuming. If it is 1, then it will be e power at only. Otherwise, it will be e power at into x naught. So that is what it has been represented here. Additionally, they have taken a input b of u. Then the additional term will come. That's it. If you have an input 0 autonomous system, then it will be e power at x naught. Otherwise, it will have some additional term that represents the influence of the input also, V matrix. Okay. So how you can represent, or if you want to expand it, how it looks like. So the problem here is representing like this in a bigger manner, it's very tedious. That's why we go to a Laplace transform simply. So that is what we were trying to explain it by giving this big equations and all. So ultimately we won't be using all this expansion, e power exponential series and all. Simply we will do the same step using the Laplace transform. That's it. So you know this. Just use this and replace this in terms of a matrix. Then you use Laplace inverse transform to find the time domain equation. Okay. So this properties of E of at simply you can use this one and formula, but otherwise you can derive this also by your own if you want to understand this better. So the simulation you can try out. It's a simple technique to understand or to visualize the system. In MATLAB, this SS represents the state space representation. TF represents the transfer function. In MATLAB, you can do this SS to TF. This will convert state space to transfer function. TF to SS, this will convert state space to, transfer function to state space. Right. We have given few examples. You can try out all those things with the basic MATLAB code. Right. Another important topics in module 10 is nonlinear system. So in real world, you used to encounter mostly. 99% it is non-linear system. Then why are we studying about linear systems so far? Because expressing the non-linear system as non-linear, it's a very difficult thing. It can, but it requires multi-dimensional representation to do a complex, really complex non-linear system. Excuse me. Okay. So, so representing a nonlinear system in terms of linear approximation would serve the purpose. It won't be exactly 100%, but you can mimic at least 95 to 96% of the system's behavior as a linear approximation of a nonlinear system. For small nonlinearities, this would be good. For example, a second order, for example, sine theta, sine term, or exponential term, or x square, x cube. So linearizing this around some point and converting or representing that nonlinear system in terms of a linear system would help you to find at least whether the system will be stable at some local points. For example, this equilibrium point, why it is very important is, if I have a bowl, so I'm just dropping a piece inside this PAX piece inside it. So where do you think it will settle? Whatever way I drop, whether I can drop it straight, drop it here, drop it there. So ultimately, it is going to settle here. You all know this by practice, right? Human know this. Some things you don't have to explain from birth. So we already know this because this has a low minimum point. So anywhere from you drop, the piece is going to settle at the bottom. So this is your equilibrium point. We call this as equilibrium point, where there is no movement between the previous state and the this state. This state. For example, your x2 minus x1 or xn minus xn minus 1 will be 0. So your x dot, can I say your x dot is equal to 0 here? So the system won't move unless you give one force according to Newton's first law. Right? That is its equilibrium point, or there are many names for it. Some, I don't remember all those things. Rest point, or people used to call it 2 3 names. So this is the idea behind it. It won't move unless you give an external force or a disturbance state. At the system state itself won't move. So for this bowl and this piece, this is the state of equilibrium point. So you have to look for this equilibrium point for all the system, and you can linearize the system around this point. So whenever I want to design a controller, I am more interested in this area than any other point, because here I don't have to give any extra energy to control or to make the system to work I want, like I want. So I would prefer this kind of state, and I would try to design a controller to do little bit of control here and there. So ultimately, I want to know where what are all the equilibrium points, and I'm going to linearize the system around this equilibrium point. The non-linearities will be approximated to a linear system around this equilibrium point. This is the idea behind this module 3, this lecture 3 of this module 10. Right. So in your class 12th or class 11th problem, you would have studied the solutions for a matrix equation, or some, what do you call, unit solution, multiple solution, no solution. You would have studied all those things, right? So we will just
Yes,
get,
ma'am.
yeah, right. Get help of those concepts here, so that you can say there are, for linear system, there are some interesting um, findings in this linear systems versus non-linear systems. If you consider a linear system, the linear system has two properties. One is, it has only one equilibrium point, otherwise it has a continuum of equilibrium point. It won't have multiple equilibrium points, but nonlinear systems can have multiple equilibrium points in addition to this. So if you take a linear system, then you can confidently say either it has only one equilibrium point, there will be one minima. There will not be any local or global different minimas. There will be only one minima, that is its equilibrium point, and otherwise it can have continuum of equilibrium point, kind of a plane, not a two different or three different or five different things. It cannot be countable. It won't be countable. It is a kind of plane of equilibrium or continuum of equilibrium. I can say for this x1 and x2, this plane would be a equilibrium points. So all the points exist in this plane will be its equilibrium. So when it comes to this set, it won't move at any point in this plane. So that is how we can represent. This is the two possibilities of a equilibrium point for a linear system. For non-linear system, we can have single equilibrium point. We can have single equilibrium point. We can we can have continuum of equilibrium point, and we have multiple equilibrium points. For example, s is equal to 2, 3, 0 can be equilibrium point. Here it is s is equal to 0, either s is equal to 0 or s is equal to or s equal to others. Now it can be like x1 plane, x2 plane kind of. Good. I think you should be clear in this to not get confused. Right. How can you find the equilibrium point? As I said here, this is the representation of its state. Its states will be equated to 0. Simple. That's it. Whatever the nth order equations you have, just equate it to 0 and find the value of the state variables. That's it. So here, if you represent the equation of pendulum here, I'm just going to equate it to 0. x1 dot x2 dot equal to 0. Then this will give me x2 equal to 0, one equation. Another equation will give me x2 minus sine x1 equal to 0. So this x2 is already 0 minus sine x1 equal to 0. So here you should be very careful. You cannot just equate x1 equal to 0. What are all the points? The sine x1 will be 0. That you have to see. So when sine 0, 0, sine 1, some variable, some value it will have. Similarly, when you go to sine pi, will it be 0 or 1? Sine pi will give you 0, right? Yeah. So sine pi will give you 0, 2 pi, 3 pi, 4 pi. So sine n pi will give you 0. So this is a kind of plane only. So whenever your first state x2 can be 0, it cannot take any other value. X1 can be 0 and pi. Both of this will be, sorry, n pi. Both of this will be its equilibrium points. So here you have multiple equilibrium points because the system is non-linear system. That's why you have 0 and n pi. Multiple equilibrium points you have. Right. Now, with this equilibrium point, what can I do? There are some other equations, unique solutions. So you can determine whether this A is non-singular or singular. If A is non-singular, then A is invertible. You will have a unique solution. For example, you have a unique point, like only one point you will get. Or continuum of equilibrium means either A is singular, it's a like one and one relation. If A is singular, you will get continuum of equilibrium. If your system has continuum of equilibrium, then A must be singular. Kind of one-to-one relationship, right? And there are some system that has no equilibrium points. So that example also it was given here. So you can go around this. Local behavior varies around different equilibrium points. Why do we need a equilibrium points? For explanation has been given here. I So linearization, you can use any of the linearization methods, Jacobian linearization or Taylor series linearization, whatever you are familiar or whatever you are comfortable with. Just use the, if I want to use a Jacobian linearization, I would take this. So x dot is equal to dou by dou x, x dot by dou y, x y dot is equal to, instead of this, I am going to use the same representation we have done so far. Your Jacobian linearized matrix would be, if I want to use a Jacobian matrix, this would be x1 dot by dou x, x1 dot by x1 dou x2, x2 dot by dou x2, sorry, x1 dou x2 dot by dou x2. Right? Find this Jacobian matrix, then substitute the, if there is a variable, substitute x equal to equilibrium point, x1 x2 equal to its equilibrium points, and then find a matrix. Then the matrix itself is the linearized representation of your state space system. For example, in this, for this pendulum, if I do, the matrix would be, if I dou x1 by dou x1 dot by x1 would be 0, dou x1 dot by x2 would be 1, x2 dot by dou x1 will be cos differentiation will be, sorry, sign, differentiating sign will give me cos. Already there is a minus, so I'm putting it as minus cos. X2 will give me minus 1. Right? I'm just differentiating this for the Jacobian matrix. And my, for now I'm going to consider 0 comma 0. There are 2 points of x1, right? 0 comma pi, x2 equal to 0. So I'm going to first do 0 comma 0, and then I'm going to do pi comma 0. So if I put 0 comma 0, this matrix would be 0 1, cos 0 would give me 1, so minus 1 1 minus 1. So this is the linearized system around the equilibrium point 0 comma 0 of the simple pendulum. So whenever the simple pendulum is kept at 0 comma 0, this is the linearized version of the simple pendulum. So when I try to do it for pi comma 0, that is upright position, this will give me 0 1, cos pi will be minus 1, this will be 1 minus 1. So this is the difference between the 0 comma 0 and pi comma 0 linearized version of the simple pendulum. Similarly, you can do it for different systems, whatever the differential equations order should be. If it is a nth order system, it would be like this: x1 x1 dot by x2 x n dot by xn. Similarly, this will be xn dot by dou x1 xn dot by dou xn. Right? So you can do it for multiple order equations without any effort. Extra effort, maybe. Like this, we call it as local linearization, because we are just seeing how the system will be at that particular point. So some example they have given, predator prey model. So you can plot this and you can write your own MATLAB code to visualize this, how the face portrait will look like. Face portrait is a system's possible trajectory, that's it. And you can see the equilibrium point. If all the arrows comes to a single point here, for example, if the all see, this comes inside, right? That is circling around and coming inside. So arrows will go towards the equilibrium point. If it goes above, sorry, um, stable equilibrium point. There are some concepts, again, I don't know whether it is there in your syllabus. We have the differentiation of equilibrium points also. Equilibrium points, we studied what is equilibrium point and how to find it. We used to study whether it is stable, unstable, saddle, and different types of representation of the equilibrium points or behavior of the equilibrium points will be studied for a nonlinear systems. So I think you won't have it here. So just this phase portraits will go, all the arrows will go towards the stable equilibrium point. So we will know whether the equilibrium point is stable or not using this phase portraits, this kind of representation. We call it as phase portraits. So you can plot it and see if it goes like apart from, how do you call it, away from the particular equilibrium point, then we call this as an unstable equilibrium point. If one point, if from one side if it is coming, from other side it is going, it is a saddle point. So similarly we used to study all the behavior about this equilibrium point. It's an interesting topic. If you take a nonlinear system course, you would be able to study all these things. Right, we have seen all the modules. Just I want to familiarize yourself with some little problems. So we can solve few problems, and if you have any doubts, we can see. Otherwise, we can wrap up. Okay, we can do one electrical based problem. As we do for transfer function, we will do for state space representation, so that while you revise your whole chapter, you can make use of both of this. R1, L1, C, C, L2 should be your R2, VI, right, minus plus here I. This is the output you want to expect. The question is, consider the system shown below, where VA is the input voltage, V naught is the output voltage. State space representation, they are asking. Find the state space representation of the system. You can either use the way you want to solve for transfer function, just find the transfer function and use your nth order and assigning variable to find the state space. Otherwise, we can go straight away. You can jump from differential equation to state space that we can see now. Right. Here, the state variables are it is our interest. So whatever it is giving proper information, we are taking that as a state variables. Oh, forgot to give you this, right? IL1. Whatever it is flowing through this. Whatever it is flowing through this is IL2. Right. First we want to apply, let's start. Applying KCL to this network at capacitor junction. Okay. So whole IC capacitor current would be whatever current it is flowing to IL1 and whatever current is like it is like splitting here and here. So I can write IC as the current through the capacitor as current that is remaining that when came from IL1 and went to IL2. The remaining one will flow through the IC. Now I'm just going to represent this in terms of a voltage. So rewriting it, I equal to C dV by dt. So representing it in terms of voltage will cost me like this, and I'm keeping it like this. Now this differentiation I'm going to write in terms of dot, because in state space form we need it in terms of differential equations, right? That's why IL1 minus IL2. VC dot will be 1 by C IL1 minus 1 by C IL2. Right. Now I have this one point. Keep this aside. Now I'm going to use KVL. as we already done in transfer function. Just Vi will be R1 into I L I L di by dt, dil1 by dt, right? So this will be R1 into I plus L1 dil1 by dt plus Vc. But this is in series, so whatever current it is flowing through here will flow through here also. So instead of I, I'm just going to write it in terms of IL1 also, IL1 itself, right? For ease of consideration. Then keeping this here because I need it in terms of differential equations as I did in the previous step. R1 IL1 plus Vc minus Vi. So this will give me Li IL1 dot R1 IL1 plus Vc minus Va. IL1 dot equal to R1 by L1 IC IL1 plus Vc minus Va. Oh, sorry, by L1 by L1 because it is common for all. Now writing KVL for the second loop, what I will get starts with Vc. It comes here, it will be Vc and it will be L2 DIL by D2 plus R2 IL2. Right? It may Vc equal to L2 DIL2 by dt plus R2 IL2. Now just going to do the same, but skipping the step by dt, this will come here, R2 by L2, this will be, right? Yeah. L2 IL2 minus Vc by L2. I think it is correct. IL2 dot is equal to R2 by L2 IL2 minus Vc.
Ma'am, I think somewhere plus minus, like it should be minus R2 and VC should be plus.
Okay, Vc, yeah, I'm keeping L2 here and R2, I'm bringing it here, right? Okay, thanks. Okay, right. Now I have three equations. This one, and already I have Vc dot. Now I'm going to write it together. So one equation, second, third. Three equations I have. That's what we want. Now I can write this in terms of state space representation. So this will be Vc dot equal to 1 by C IL1 minus 1 by C IL2. IL1 dot equal to R1 by L1 IL1 plus Vc by L1 minus V1 by Vi by L1. IL2 dot is equal to minus R2 by L2 IL2 plus Vc by L2. So I've just written in terms of this to write it easily for state space equations. Right. Just rewriting in terms of a matrix. Vc dot IL1 dot IL2 dot is equal to 1 by C minus 1 by C. Three states should be there, right? VC it's a one state. So where can I keep VC? Since VC comes here, I'm going to keep VC there. So To avoid confusion, I will write the state matrix first. VC dot IL1 dot IL2 dot. This is the left hand side. Similar to X dot equal to, there will be some matrix VC IL1 IL2 because these are all the states we define. The input matrix will come again. VC, there is no VC in the first equation, so I'm keeping it 0. 1 by C minus 1 by C, right? So 0 into VC, 1 by C IL1 minus 1 by C IL2. It comes properly. The second equation should be my R1 by L1, 0, 1 by L1, right? I'm just leaving it here for now. VA, I'm leaving it. I'm going to write it later. IL2, there is no IL1 term, minus R2 by L2.
Ma'am,
Yeah,
in the second one, it 0 will come first and R1 by L1 will come after that.
0 will
Because
come for second one. IL1, oh, okay, huh? Right. IL1 is the second state, right? Yeah, correct. 0, R1 by L1, right? So third state will also be wrong.
first one will be 1 by L1, third one will be 0.
Yeah,
Because
right.
IL2.
Yeah, VC should come first because 1 by L1 should L2 comes first. 0 minus R2 by L2. Am I right?
In second one, I'm saying that first 1 by L1 will come for VC.
VC. Yeah.
0 is
I'm just thinking that VC will comes last. Okay. 1 by L1 will come first. IL1, there is no IL2. Now I have left VA there, right? So in first equation, there is no VA. Second equation, 1 by L1. Third equation, there is no VA. So VA is your U. So here U is equal to VA, X is equal to VC, IL1, IL2. So these are your state and is equal to VA. So this is your input. So this is the correct option. Good. So similarly, when we come with from this equation, what we used to do in transfer function is that we will do this and use Laplace transform and convert it in terms of S and write it in terms of transfer function in terms of S cube plus S some S square, some VAS1, something like. So now we just cut that off in a particular step and then we convert it in terms of differential equations. But you can do the same. You can write it in terms of transfer function and then convert the transfer function to state space. That is also allowed if you are comfortable with that. Otherwise, you can do this. Whatever way you are okay with that. But learn both the methods because it will be easy to solve that similar kind of problems. Okay. Good. Now, I'm going to ask another good question. That is, G of S, I'm giving you a transfer function 21 by S plus 5. I'm going to give 4 state space equation or representation. You have to tell which representation is correct. First one is x dot equal to minus 5x plus 3u, y equal to 7x. B would be x1 dot, x2 dot equal to minus 5, 0, 0 minus 1, x1, x2 plus 3, 1, y equal to 7, 0, x1, x2. C is x1 dot, x2 dot minus 5, 0, 0 minus 1, x1, x2 plus 3, 0, y equal to 7, 3, x1, x2. T would be x1 dot, x2 dot equal to minus 5, 0, 0 minus 1, x2 plus 3, 1, y equal to 7, 3, x1, x2. Right. Now, this is the question. Just try to solve this, convert this transfer function to a state space equation and tell me whether which of the following is correct. You have the formula for it, right? To convert state space to, sorry, transfer function to state space. So we can use it, is easy method. Instead of finding all these things, we can go from solution to question. What is giving us, because we know the equations. So will g of s will be c into si minus a the whole inverse into b plus, since there is no d, I'm just going to leave this plus d. So okay, this will be 0. So first put the first a value here. C is 7, right? Si minus a the whole inverse into b will be your 3. So this will give me si minus a inverse. Oh, a I didn't write what I say. A is your 5. 5. Okay. This gives me s minus 5 inverse into 3. Uh, what is s minus 5 inverse? A is minus 5, right? It's s plus 5. What is s plus 5 inverse? It will be 1 by s plus 5. So 7 into 3, 21 by s plus 5. Does it give the question? Is it correct? Can
Yes,
we, yeah, can we choose A option? So A is the correct
yes,
option, right? Instead of leaving all other options, we will check other again with the other options also. So for the option B, C will be 7, 0, C into Si minus A. So A will be this, S minus A means S plus 5, 0, 0, S plus 1, inverse into B. B is 3, 1. Okay. Now what you will get? You will get 7, 0. Take a determinant, s plus 5 into s plus 1. I'm just keeping as it is. So when so it will be adjacent, then this will be s plus 1, s plus 5, 0, 0 by s plus 5 into s plus 1, right? Inverse. Adjacent by determinant. Give me 7, 0, 1 by s plus 5, 0, 0, 1 by s plus 1, 3, 1. And this is 7, 0. I'm keeping it like this. So we 3 by s plus 5 plus 0. 2 cross 2. This is 2 cross 1. You will get 2 cross 1 as output. 0, 1 by s plus 1. This will give me 7, 21 by s plus 5, 0. So why it is giving same? So should this be, B answer should also be same.
yes,
So this is the MCQ, MSQ, right? Okay, we'll try out the third equations also. Minus 5 is 0. Sorry, what is here? C, 7, 3. C, Si minus A. A is here. Minus 5, 0, 0, 1. So this would be S plus 5, 0, 0, S plus 1. And your 3, 0, right? B value is 3, 0. Okay. So similarly, your inverse, we already found it. 1 by S plus 5, 0, 0, 1 by S plus 1. 7, 3, 3, 0. So will give me 3 by S plus 5, 1 by S plus 1, 7, 3, 21 by S plus 5. This is not a right answer. Okay, C is not a right answer. Oh, sorry, this will be 0, right? So this will also be 0. So 3 is also a right answer. What about the fourth option? Fourth option will also be, might be the right, I think. Okay, this is not the right option. But all the first three options, A, B, C, are the right options. But you have only one transfer function. How will you get these three right options? That's what state space representation in general are not unique. A single transfer function can have multiple state space representation. It's like linearly dependent. You will have one base and you can represent it, maybe 1, 2 can be represented as 2, 4, can be represented as 4, 8, right? So it can go ahead. So similarly, the state space representation for a single transfer function is not unique. We have to keep this in mind. To study that, we took this example. We will solve one question in linearization. Okay. Consider the following nonlinear system. X1 dot x2 dot equal to u square minus x1 plus y into 1 minus x1 square x2 plus u. First is equilibrium points. How do you find equilibrium points? Just equate x1 dot x2 dot whatever state space you have, equate it to 0. So this will give me x2 plus u1 u square is equal to 0 minus x1 plus 5 into 1 minus x1 square x2 plus u equal to 0. Right. When for this input kind of system, consider input is equal to 0. So this will give me x2 equal to 0 minus x1 plus 5 into 1 minus x1 square x2 equal to 0. So x2 is already 0. Wherever there is x2, you can put 0. x1 plus this term will go to 0 equal to 0. So x1 will also be 0. So the equilibrium points here are x1 equal to 0, x2 equal to 0. So this will be x star. Usually we represent this equilibrium point using star. So this is x1, this is x2, right? 0, 0 are the equilibrium points. The second question is to linearize the system around its equilibrium point with u equal to 0. Second question is linearize system around its equilibrium point x star with u equal to 0. Right? They already given u equal to 0. So we will have, I will rewrite the equation here to, this is the equation, here it is. Equating it to x1, there is no x1, x2 minus 1, x2 will be, oh, there is x1 not there, right? So will be minus 1 plus minus 10x1, right? 10x1, x2. The equation would be x2 equal to 0 minus x1 plus 5 minus, 5x2 plus 5x2 minus 5x1 square x2 equal to 0. Now if we linearize 0, 1, x1 will be minus 1 minus 10 x1 x2, x2 will be 5 minus 10 x1 x2. Sorry, 5 x1 square only, right? It is only single variable. 5 minus 5x1 square, that's it. We have to linearize it around 0, 0 because our equilibrium point is like that. So when I put x1, x2 equal to 0, 0, it will be minus 1, 5. So this is my linearized system around 0, 0. Can you repeat? It is not clear.
That 10x1 x2 term.
How it comes?
Yes, ma'am.
Okay, okay. Right. We have this equation, right? Minus x1 plus 5x2 minus 5x1 square x2. So when I differentiate this whole using the dou f by, for example, this is f, dou f by dou x1. So dx by d, sorry, d by dt of dx of x will be 1, right? So this will be minus 1. d by df by dx1 is 1, minus 1. Since it is minus, okay, wait. d by dx1 of x1 will be 1. Since there is a minus, it will be minus 1. It is clear?
Yes, ma'am.
Alright. Then again there is a x1 term here. So when I differentiate dx1 x1 square, this will give me 2x1. So differentiating minus 5x1 square will give me minus 5 into 2 into x1. This will be minus 10 into x1. Already there is another variable which is multiplied with that. So we have to write it as it is. We don't have to remove that for the first equation. Since it is in a multiply. If it is a minus 5x1 square plus x2, then differentiating x2 will, in terms of x1, will go to 0. Since it is multiplied, I'm just keeping that variable as it is. Again, when you differentiate with respect to x2, you will get same equation x2. The first term, differentiating x1 by x2 is equal to 0 because those are two different variables. So this first term, when differentiating with respect to x2, will go to 0. Then again, differentiating 5x2 divided by x2 will give me 5, right? Ax differentiation will give me a. So this will be 5. Again, there is an x2 here, but consider this as a coefficient of x2. So here d ax by x dx will be a. So here d of minus 5x1 square, consider all this as a, into x2 by dx2. So this will give me a, right? Minus 5x1 square as it is. That's why this is minus 5x1, sorry, minus 5x1 square. Clear or have doubt?
Yes, ma'am. Clear.
That's why I have written 5 minus 5x1 square. Here it is 1 minus 10x1 x2. Minus 1 minus 10x1 x2. Right. I'm just substituting x1 x2 as 0 0. So you will get a matrix like this. That's it. This is the linearized form of your non-linear system around its equilibrium point. Now, the third question they are asking is, what is the pole of the linearized system. Not for a non-linear system, this is a linearized system. So what is our linearized system? We have this 0, 0, minus 1, 5. This is our A matrix, main matrix. So if we find the eigenvalue for this matrix, then we will get a pole. That's what we learned so far. So, sorry, not A, eigenvalue of S minus A. Okay. Now, this will give me eigen of x minus si minus A I want to find. Now this Si minus A, if I find a determinant, this will be 0. So if I find Si minus A would be S, 0, minus 1 will be 1, S minus 5. If I take the equation S square minus 5S plus 0. Oh, okay. I think I made a mistake. 1 it is there, no? 1 will be here. This 1, there is no variable here. So this will also be 1. So if it is 1, this will be minus 1. Si minus A will be minus 1. So this will become minus 1. Minus of minus 1, this will become plus 1 equal to 0. Because this is a 1 term, minus of minus 1, this will become like this. That's why it is plus. Good. Now this is my characteristic equation. If I find the poles out of it, then minus b means plus or minus b square 25 minus 4ac minus 4 by 2a. 5 plus or minus root 21 by 2. How can I split this? Anytime I can split it properly. No, right? 7 into 3. Nothing is under root. So I'm just keeping it like this. Plus for 5 plus or minus root 21 by 2 are my poles of the linearized system. Just find Si minus A and find the determinant of it. It will give you the poles of the linearized system. Right, that's it. I think that's it. I have prepared for you to teach. If you have any doubts, you can ask me. Otherwise, we can wrap it up.
Right now, I don't have any. Ma'am, can we get practice assignment solutions for week 5 to 8?
Week 5 to 8.
Yes,
Okay, I will check
because
with the
they
team.
are a bit difficult. Like I was not able to solve all of this.
Okay, I'll check with the team and let you know. I'm not sure about it, whether it is available or not. I will check with the team and professor and let you know. Okay. Okay. If there is no doubt, we can leave.
Thank you.
Thank you.